Okay, so good morning, everyone. So let's start our lecture. So we have these multiple choices you received some times ago, so we can start by working on those. You can ask any question, doubt, or remark you have about what we already did in the chat. And if you don't have any doubt, question, or anything else you want to discuss, I'd like to see what option you deem to be correct among these A, B, C, D. So just write your favorite answer in the chat, and then we'll do that together and see what we get. Okay, so we have someone, Camilla Tetti, saying that B is her favorite option. I'd like to wait for a little bit more people to express their idea before discussing it together. So here we are with these metrics. Well, linear mapping actually from R3 to R3. We have its characteristic polynomial, and we have to decide among the options. Okay, so seems that option C is more liked. Just keep in mind that knowing the characteristic polynomial, so this does not fix F or M. So P of X does not, well, here probably is also P of T. P of T does not give the matrix or the linear map, meaning that different matrices, different linear map can have the same characteristic polynomial, right? So just be aware of that. There are different matrices, 3 by 3, having that characteristic polynomial. And I can provide you some examples of this. So for example, 0, 0, 1. And then whatever I put here in the, say, yellow area, whatever I put here, the characteristic polynomial is going to be the one you see there. So these are examples. And there are many other examples for which the characteristic polynomial is that one. And now you have to find the statement which is true. Okay, so I suggest we go through each statement one by one and see what we think to be the correct answer. So let's have a look for A to A. So A is saying that the dimension of the image of F is equal 1, implies that F is simple. Remember that simple means that if you choose a basis in R3, then the associated matrix with respect to that basis used twice is diagonalizable, right? So simple means that chosen A basis, the associated matrix to F is diagonalizable. Okay. Now, if the image has dimension 1, what does it mean? Well, this means that the kernel will have some dimension, right? Because the dimension of the kernel plus the dimension of the image must be equal 3. So if this number is 1, this means that the dimension of the kernel is equal to. Okay. Sophia Carnot made a nice connection because she said, well, if the dimension of the kernel is 2, we have to remember that the kernel of F is the eigenspace of 0. So what we are saying is that the dimension of E0 is equal to, and look, this is the multiplicity of 0 as a root of the characteristic polynomial. Look here, right? And also, we have another eigenvalue, which is 1. And what is the dimension of the eigenspace of 1? What do you think? So what is the dimension of E1? Can you tell me? Use the chat. It is 1, because it is at most the multiplicity of 1, which is 1. It is at least 1, so it must be 1. So the dimension of E1 is equal 1. And so we are in this situation in which the eigenvalues are such that the dimension of the eigenspace is equal to the multiplicity. And so, yes, F is simple, M is diagonalizable. So what we saw here is that the eigenvalues are in R, and the dimension of E lambda I is equal to the multiplicity of lambda I for I equal 1 and 2. And this is what it means to be simple. So F is simple. Okay, so the first option is true. Okay, here it is. Now, some people said option C. Option C seems to be one really liked option. Now that we saw that it is not true because only one option true should exist, can you see why this is not true? Can you tell me why? So where the mistake was? For example, you know, Salvatore Lagrasta, Andrea Grasso, other people who thought C was correct. Can you see what was the problem with that? Can you see why is that false? Exactly. So the point was, well, overlooking the fact that the kernel is the eigenspace. So you see that having the dimension of the kernel equal 1, so this statement here actually says that the dimension of E0 is 1, which is strictly less than the multiplicity of 0. And so this means F is not simple for sure, right? Good. That's nice that now we have an idea of why it is not true. Okay, good. Now, can you tell me why D is false, for example? Can you tell me why D is false? It's a very silly question, but we don't want to learn, to revise, and to learn how to play this game. So can you tell me why D is false? Exactly, because 4 is not a root of the characteristic polynomial, so it cannot be an eigenvalue. Good. And now, can you tell me why B is false? what is the problem with B? Where is it coming from? Salvatore Lagrazia says 0 might have multiplicity 2. Well, 0 has multiplicity 2. Sophia Carnau says, well, there could be less than 2 linearly independent eigenvectors. 3 distinct eigenvectors, but we have only 2 eigenvectors. Walter Girotti, this is wrong, because remember, the eigenvectors are always infinite, right? Because when you multiply them by any scalar, but that's not to be sorry, just be careful. There are always infinitely many. The point is that you see the crucial part is that they speak about independent. So linearly independent eigenvectors. So what could be the problem? Well, the problem could be, for example, for option B, if you have a matrix like this, a very simple one, right? This matrix A, it has characteristic polynomial 0 minus t square 1 minus t. So is exactly the one we before. We see immediately because it is triangular, right? Now, can you compute the dimension of E0 in this case? Can you compute the dimension of E0 here? Without computing E0, what do we have to do to compute the dimension using A? Yep, so you computed E0, that's fine. But can you tell me the dimension in a very quick way? What is the dimension by Rouchet-Capelli theorem? It is what? 3 minus the rank of A, minus the eigenvalues times the identity, right? So just rank of A. And no doubt that the rank of this matrix is 2, because it is row reduced, right? You have just to make a row swap if you want, 2 non-zero rows. So this number is 1, which is less than the multiplicity of 0, which is 2, as you see from here. And so what is this telling me? Well, this is telling me that if I want to find linearly dependent eigenvectors, I can only find 2, because we can make a picture, if you want, of the situation. We are in R3, and for this matrix here in this example, there are 2 eigenspaces. The eigenspace of 0, we just computed, is a line, and then the eigenspace of 1, which is another line. So there are only 2 lines as eigenspaces, okay? And so I cannot find 3 linearly independent vectors subject to the condition that they must lie in E0 union E1. Or in other terms, E0 plus E1 is not R3. It's just a plane, okay? Okay, good. There is not much to explain about the kernel being the eigenspace of 0. It's just a definition. Let's make a note so we will remember. The eigenspace of 0 is the kernel of the associated matrix minus 0 times the identity. So it is the kernel of the associated matrix. And this is the kernel of the linear map, right? So this is why this is true. Okay, good. Now let's move to the second one. And just to be sure that we all understand this equality and this equality work on a canonical basis, so we don't get confused. What is always true is that the dimension of E0 is the dimension of the kernel of M. This is always true, but if you want to have equality as eigenspace and kernel, well, you must use canonical basis. Okay, now let's move to this new one, and let's see again what are your preferred options, A, B, C, or D, and see then how to go through these cases. Okay, Sofia Karnauk suggests A. Let's see if some other people have some ideas about this. So it is a linear map, endomorphism, from R5 to R5, having a given characteristic polynomial. And we want to find a true statement relating the dimension of the kernel and the dimension of the image. So the idea is that the rank nullity theorem must be used. So that's the idea. So dimension of the kernel plus dimension of the image must be equal 5. So this is probably part of the solving process, but we have this information about the characteristic polynomial. Okay. So, for example, Alireza says something about the kernel, which is, sorry, the eigenspace of 0. Since 0 is not an eigenvalue, so 0 is not an eigenvalue. And this means that the dimension of the kernel of F must be 0. So this is telling me that these two are clearly false. So I have a 0 here. And so you see there is only one possible option. Oh, sorry. I made a mistake. I'm sorry. Let's take it back. The characteristic polynomial is written in a deceiving way, and I was deceived. So you see it is minus t squared minus 3, t squared minus 1, t. So 0 is an eigenvalue. Yeah, 0 is an eigenvalue. I'm sorry, so it was a stupid remark on my side, of multiplicity 1. So the multiplicity of 0 is equal 1, and this is greater or equal than the dimension of E0, which is greater or equal than 1. So this means that the dimension of E0 must be equal 1. And this is the dimension of the kernel. Yeah. And so this is why the first option is correct. So we don't need to use not even the rank nullity theorem. It's just the fact that the kernel has dimension 1. So if the kernel has dimension 1, the image will have dimension 4. So these two are false. And since the dimension 1, also the last one is false. Okay, this was an easy one. Okay, let's move to the last one we had in the row. Yeah, here it is. So we are giving an endomorphism. We know something about its kernel. We know something about an eigenvalue. And we want to know which statement is true. Okay, so let's see how can you do this. How can you work out which one among A, B, C, and D is correct? Okay. So in the meanwhile, I'm looking in the chat. Sara Bodrone speak about the previous exercise, which I think is this one. Yes, and she asked, what is the dimension of the image? Why do you say 3, Sara Bodrone? Can you explain why you say the dimension of the image is 3? You should have a look to the rank nullity theorem, the yellow expression, well, written in red and yellow highlighted. From those relation, from that relation, you should be able to deduce what is the dimension of the image. Okay, I see. No problem. The fact is that you see, since the dimension of the kernel is 1, and 5 minus 1 is 4, the dimension of the image is exactly 4. Okay, good. Let's move to the next one. So what can you say about this one? Which option do you prefer? A, B, C, or D? So Cesare Piemontese, in the meanwhile, has a question. If 0 is not an eigenvalue, what can we say about the dimension of the kernel? Tell me, what can you say? So try to argue like this. If the dimension of the kernel is, for example, equal 1, what can you say about 0 being an eigenvalue? Try to argue in this way. If the kernel has dimension 1, 2, 3, 4, 5, what can I say about 0 being an eigenvalue? So what you should do is take an element of the kernel, and what is f of that element is 0. So it is 0 times v. And so v is an eigenvector if it is not 0, right? So having some non-zero vector in the kernel means that 0 is an eigenvalue. So let's make a note, not related to this multiple choice, but in general. You see, if the dimension, well, let's do like this. If the kernel of f is different from 0, you know, the 0 space, this is equivalent to say that lambda equals 0 is an eigenvalue. Simply because you take an element here, different from 0, you compute f of v, you get 0, which is 0 times v. And this is exactly the definition of being an eigenvalue. Right? Good. So about this multiple choice, looks like that D and B are the preferred options. So let's wait for a little bit more people to take part. In the meanwhile, Cesare Piemontese, let me know if I answer your question. Okay, good. So yeah, B and D seems to be the one you like the most. B and D. Okay, so probably I should ask, why do you think that A is false, for example? So why do you think that A is false? What is the reason why no one is selecting A? This is just an honest question, right? It's not that I want to imply that A is the one you should choose. It's why do you say A is false? Okay, Salvatore Lagrasta says the dimension of the kernel, let's do like this. The dimension of the kernel of F is equal to the dimension of V. And V, I hope you see, is a plane in 3 space, so it has dimension 2. So having dimension 2, it means that the dimension of E0, which is less or equal to the multiplicity of 0, this number is 2, and so it means that the multiplicity of 0 is 2, right? Good. Then we also know that -1 is an eigenvalue, so we also know that the dimension of -1 is greater or equal than 1, less or equal than the multiplicity. But since the sum of the multiplicity is the degree of the characteristic polynomial, so it is 3, since this one is 2, it must be that the multiplicity of 1 is 1. And so there cannot be other eigenvalues, right? Because otherwise the degree of the characteristic polynomial should be larger than 3. So this is why this is false. Someone has an idea about why C is false. The characteristic polynomial of F can be minus t times t plus 1 square. And someone says 0 is not an eigenvalue. Well, 0 is an eigenvalue. What was that? R fanfare. 0 is an eigenvalue. Okay. Let's see someone say why C is false. Okay, Salvatore Lagrassa says because in the polynomial you see here, the multiplicity of 0 is 1, but it must be 2. And so this is why this is false. Okay, then we are left with B and D. So Beatrice Grassano says that C and D imply themselves. If it is true, then they cannot be both right. So this is a way to see why D is false. But you should tell me why D is equivalent to C in your opinion. Sofia Carnaut has a way to say that D is false because she says that the dimension of the image should be 1. Well, since the dimension of the kernel is 2, by the rank nullity theorem, I know that the dimension of the image plus the dimension of the kernel must be equal, we said 3, right? Since this one is 2, this means that the dimension of the image can only be 1. So this is why D is false. Yes, I agree. That's a way to say that D is false. So we are left with the fact that F must be simple as the only possible true option. And why is it true that F is simple? Well, it is simple because from what we saw here, there are 2 eigenvalues, 0 and -1. The dimension of E0 is 2. The dimension of E1 is that equal to the multiplicity, so can only be 1, sorry. This one is equal to the multiplicity of 0, and this one is equal to the multiplicity of 1. Sorry, minus 1. Okay, so repeat it. So since the eigenspace of 0 is dimension 2, the multiplicity of 0 it is at least 2, cannot be 3 because there is another eigenvalue, so it is 2, the eigenvalue, so must have multiplicity exactly 1, so the dimension is equal 1. So the condition is satisfied also because the eigenvalues are both real. Beatrice Grassano is explaining why she said that C and D are equivalent. And she says, because if C is the characteristic polynomial, yes, the dimension of the kernel would be 1, and the multiplicity of the image would be 2. Perfect. So very well done. So Beatrice Grassano says, if you have this, you have that 0 is a simple eigenvalue. So this means that the kernel has dimension 1, and so the image has dimension 2. So C implies D, and so C cannot be true. Otherwise, also D would be true. Yeah, very nice, perfect. Dimension of E0 is 2 because E0 is the kernel. And V, you see here, is a plane in R3 going to the origin, so it's a subspace, and it has dimension 2. Okay, good. Let's move on now to our, well, first, any further doubt, question, or remark about this? If not, we can move to the next exercise sheet we have to cover, which is this one. So we have to cover the exercise sheet for 21 and 22. Here it is, yeah. So I start with one proposed exercise for you. It's a little bit of mix of theory and practice. Say P, R, N, N, a matrix with real entries, n times n, orthogonal if and only if the rows of P are a orthonormal basis of Rn. And similarly, it is true for the columns. Okay, so let's see how you can do this. For example, I suggest you try for n equal 3 and see that it is true, and then we try to extend it for any n. So I just want you to play a little bit with this very quickly and tell me what you believe to be the way to do this. So orthogonal if and only if the rows and the columns are a orthonormal basis of the appropriate space. Okay. Kate Balchi says, well, what does it mean to be orthogonal? It means that when you multiply a matrix, P by its transpose, you get the identity. So what does it mean? It means that if I look at P as a collection of columns, for example, when I multiply P transpose P, what I'm doing is taking these columns that now are rows, and I will get the identity matrix n times n. And what does it mean about the dot product? So Ci dot Cj, what is this going to be? So this equality was telling you about the dot product Ci dot Cj. Well, we should remember that the ij entry is equal to ci dot cj. So this is going to be 0 for I different from j, and 1 when they are equal, right? And so this is exactly what happens. This means that C1 Cn is orthonormal, right? But now let me ask you, is it a basis? What do you think? Is it a basis? Yes or no? And if you say yes, why is it a basis? Okay, Sofia Karnauk says because there are n linearly independent vectors. That's very nice. Paolo Lovera, I don't really understand what you mean because anything is a linear combination of E1, En, right? So if you just say that, you would say that any set of vector is a basis because they are a linear combination of E1, En. So probably you didn't express rightly in the proper way what you think. Sofia Karnauk says that they are linearly independent, and that's true. So the answer is yes, because it consists of n, and n is the same number you have here, linearly independent elements. But why is it true that it is linearly independent? Well, because you write down A1 C1 plus AN Cn, you set it equals 0, and then you play the game of the dot product. So I dot product these by Ci, I will get 0, right? And if you compute at the left hand side is going to be AI. So this is why they are linearly independent, because if you have a linear combination which is 0, each of the coefficients must be 0 since they are orthonormal. Okay? Good. Same holds for the rows. Okay? So this is how you describe orthogonal matrices, sorry. They come from orthogonal basis, orthonormal basis. Okay, now we want to know can we find P orthogonal such that A is equal to P well, let's make it in this way, in such a way that P transpose A P is a diagonal matrix. For A equal to 1, 2, 2, 1. Can we do this? What do you think the answer is? Yes or no? Sofia Carnauck, be careful, symmetric and real, right? So, yes, because A is real and A transpose is equal A. So we know that if you go and do this, you will find orthogonal eigenspaces and so an orthonormal basis of R2. And using that, you will produce a orthogonal matrix. So if you go and compute, you will find eigenspaces E of lambda 1, E of lambda 2, and then you will construct P by taking a vector, say V1 and a vector V2, Vi in E lambda I of magnitude 1. And the matrix you construct in this way will work because if you compute, you will get that AP, remember, is going to be AV1, AV2. So it's going to be lambda 1 V1, second column lambda 2 V2. And if you multiply by P, the diagonal matrix lambda 1, 0, 0, lambda 2, you will get again lambda 1 V1, lambda 2 V2. And so you get that these two are equal. And so you get that P transpose AP is equal to a diagonal matrix, right? So you get P transpose AP is equal to the diagonal matrix D. This is just to make a short recap, okay? Okay, now we ask the same question, but for a different matrix and see what our answer is going to be. So, and let's see what our answer is going to be for a different matrix. Here it is, say 1, 2, minus 2, 1. What do you think? Can we do this or not? Okay, so Sofia can now say no. Walter Girotti says, well, the eigenvalues are complex. Well, if they are complex, then you cannot find those matrices over the real. But, right? So if the eigenvalues are complex, you cannot find those matrices over the real. So let's see. Let's write down the characteristic polynomial. It is x squared. Then the trace is minus 2x. The determinant is 1 plus 4, which is 5. So the discriminant is b squared, 4, minus 20, negative, complex eigenvalues. And so P and is not real. So P is not real 2 by 2, okay? And also the diagonal matrix is not real. Okay. Let's also make a note, because we can change this a little bit. So what if we, so this is a nice answer, but what if we do like this? Sorry, I made it. This is not what I want to do. So suppose we do like this. And we ask the same question. Maybe let's put a 3 here, so we change it a little bit. What do you think? Can we do this or not? Can we find the matrix P? If you do the computation in this case, you will see that the characteristic polynomial is x squared minus 6x plus 9 plus 1, which is 10. Is this correct? 3 and 3, 9. Okay, so this is not the example I want, because the answer is going to be the same. So we want to do something different. So let's say how we can make this work. So we want real eigenvalues. Okay, now I know what to do. Yep. So let's change it a little bit. Sorry, let's change this matrix B in the following way. Say that it is something like 3 minus 3, 3 minus 3. Okay, and we want to know if we can make it into a diagonal matrix by multiplying by a orthogonal matrix. Can we do this? Yes or no? And here you see what is the difference. The difference is that the characteristic polynomial now is nicer. It is x squared, and that's it. So there are real eigenvalues, right? But can we play that game with the orthogonal matrix P or no? What do you think? Sofia Kanauk says no. And why do you say no? Do we have a way of explaining why you cannot do that? Okay, yeah. So the answer here was no. And the answer is again no, because B is not diagonalizable. Okay, good. So we finished this with one note, which is the following. So if your matrix P transpose AP, P orthogonal, right? So if you have this equality, then of course it is diagonalizable, and it is also true that P diagonal P transpose, you have this situation, and this means that if you compute the transpose, this is going to be P diagonal transpose P transpose, which is equal P diagonal P transpose, which is equal A. So you see, in order to be able to have the matrix orthogonal doing this, the matrix must be symmetric. Otherwise, you cannot do that. Okay? Good. So next one, orthonormal basis and Gram-Schmidt algorithm. So say compute an orthonormal basis of, here it is, linear span of 1, 2, 2, 1, 1, 1. So compute it and let me know. Just the first who managed to compute it, just pop your answer in the chat. The question was to find an orthonormal basis. And to answer Sophia Carnot, you can use whatever method you want. So probably everyone will say, well, once you realize this is just R2, you just pick the easiest canonical basis of R2, sorry, the easiest orthonormal basis of R2, which is the canonical one, right? So very simple. And the idea is always do not start with algorithms or procedure, just think about what you're asked to do. Sometimes it's easier than you think. Okay, so let's see another one of this kind. So compute an orthonormal basis of this one. So V, X, Y, Z, T. So we are in R4 such that X plus Y is equal Z minus T is equal X plus Y plus Z plus T equals 0. So let's see what you can do with this. Let's see how you can find the orthonormal basis of this one. Okay, so we have the first proposed solution by Salvatore Lagrasta and Sofia Carnau. So let's see together, right, how we can do this. So first, we need to find V, which looks like the kernel of some matrix. Let's see if I can write this correctly. So it is 1, 1, 0, 0. Then it is 0, 0, 1, minus 1. And then it is 1, 1, 1, 1. Okay, because it is the solution set of a linear system of equations having three equations, which is like this. And by using row equivalence, this is the kernel of 1, 1, 0, 0. Then we still have 0, 0, 1, minus 1. Now I change the third row by using the first, subtracting. And then I change it again. So I change again the last row by, say, subtracting the third. So we get something like this, 0, 0, 1, well, sorry, 0, 0, then should be 2, but then we put a 1. Okay. So this means that the dimension of V is equal 1, right? So if you look at the answer we got, there is something off because they look like 3 vectors. So it's probably too much. Maybe you computed something different, Salvatore Lagrasta, Sofia Carnau. What did you compute? Can you explain what you wrote is a basis of what? Okay, so you made the orthonormal basis for the row space of the matrix. We can speak about that in the second, but let's just do the one we were asked to do, right? So what is the kernel here? Okay, so Alberto Eusebio got an expression for V, which is fine. And so to get an orthonormal basis is very, very simple, right? So once we know what is V, so once we know that V is the linear span of just one vector, zero, 0, 1, minus 1, an orthonormal basis is just obtained by normalizing, right? So orthonormal basis is just like this. Of V. If we want, we can also play a little bit with what Salvatore Lagrasta and Sofia Carnau did, which is basically working on the row space of this matrix. So say we want to do something about the row space of this matrix. So, but this is a side thing. So this is B. I look at the row space of B, which is equal to the row space of the even simpler matrix we have downstairs, right? So, yes. And so, well, I wrote the same matrix. Yeah. So the row space of B is equal to the row space of C. So you have these 3 vectors, and you could be tempted to say, well, now I apply Gram-Schmidt algorithm to these 3 vectors. So here they are. One is V1, one is V2, and one is V3. But we can also do more. We can change a little bit the matrix. Okay, we can change the matrix a little bit more, so to make life even easier. So here is what probably you want to do. So you want to have these 0, 1 here, and you want to have a 0 there. So now the vectors we look at, because it's our choice, right, of generators, are these 3. And as you see, these 3 vectors, so v1, v2, v3, are already pairwise orthogonal, and the only thing you have to do is to normalize the first. So what Salvatore Lagrasta and Sofia Carnau did was nicely done, okay? Someone asked, how did we find V? Well, you solve the linear system of equations. That's something that now we know to do very well, so we don't spend a lot of time doing it over and over, okay? So you just solve the linear system of equations having these matrix as a matrix of coefficients. You write down x, y, z, t. T must be 0, so also z is 0, and x plus y must be 0, and you proceed in this way. Okay, let's see now a slightly different kind of exercise. Here it is. So let's say that A has characteristic polynomial 2 minus x times 3 minus x. And then we consider the following questions. First, we want to compute a square and a cube using A. So write down them as an expression involving A. And then we consider a question, are A square, A cube diagonalizable? So let's consider these 2 questions. And the idea is that you have to use Gram-Schmidt algorithm, right? So let's see how you do this. As soon as you have some ideas, you can pop it in the chat if you have questions similarly. Michele, in the meanwhile, I read in the chat. So Michele Porco says, why the dimension of V is 1? Well, because, where is it? It is a kernel, right? So the dimension of V is the usual number of unknowns minus the rank of the matrix A, which is, for example, here it is. Here is A. And so by Rocher-Capelli theorem, you have to take number of unknowns minus rank, which is 4 minus 3, which is 1. No, we cannot say that A looks like that. No, that's one possible matrix A having that characteristic polynomial, but no. And we don't need to do that, right, for the first question. So let's go and have a look at the first question since you already have some answers. So what you know is that P of A is going to be 0, and this is equal to twice the identity minus A times 3 the identity minus A, which means that A squared minus 5A plus 6 the identity is 0. So this is, for example, what gives me A squared is equal 5 the matrix A minus 6 times the identity. Okay, and if I want matrix A cube, I simply say this is A times A squared, so which is 5A squared minus 6A, right? Which is equal to 5, and then I repeat, 5A squared minus 6, the identity minus 6A, and so I work it, sorry, this is not a square, so it is 5 times 5A minus 6, the identity, and we have minus 6 outside. And so we are left with 25 minus 6, which is 19A minus 30 times the identity. So these are expressions for A squared and A cube using matrix A and the identity, okay? Which is always at our disposal. Okay, this is just to remind you about the game you play with Cayley-Hamilton theorem. Okay, now what can you say about the second question? Is A diagonalizable? Is A squared diagonalizable? And so on. So let's see what you think you can get here. So I suggest we start with A. And let's ask ourselves, is A diagonalizable? What do you think? And you can answer without knowing A. In this case, you can. Let me just remind you that we know the characteristic polynomial, right? 2 minus x, 3 minus x. Okay, you say yes, but can you tell me why is it true? Exactly, because A is 2 by 2, since the characteristic polynomial is of degree 2, right? And the fact that the characteristic polynomial is like this tells me that I have 2 eigenvalues so we have 2 distinct eigenvalues, 2 and 3, and so it is diagonalizable. Because it is 2 by 2 with 2 distinct, no, it's unreadable, with 2 distinct eigenvalues. Okay, good. Perfect. Okay, what about a square and a cube. So here the answer is yes. And what about a square? What do you think? Is a square diagonalizable? Yes, no, it depends. Alberto Eusebio says, because it is sum of diagonalizable matrices. That's not in general true. So if you take two matrices which are diagonalizable, the sum is not necessarily going to be. Here, so let's see. We know that A is diagonalizable. And so can be written in the form P minus 1 diagonal, sorry, can be written in the form P diagonal P minus 1. Okay, so if you think in this way, then A square, it is P d P minus 1, P d P minus 1. So it is P d square P minus 1. And so A square is diagonalizable, right? Because what is true is that the product of diagonalizable the powers of the diagonalizable matrix are diagonalizable, okay? So an is going to be diagonalizable for all n. So let's try this down. Note A diagonalizable means am diagonalizable. Let's make another note, since some of you say A, B diagonalizable does not imply that A plus B is diagonalizable. And you can easily find example like this. So something of this kind. Let me think for a second. So you can do this, and then you can do this, and the sum is this one, right? So this one is not diagonalizable, but this one and this one are diagonalizable because they have distinct eigenvalues. So these two are A and B. They are diagonalizable, but the sum is not. What is true is that the powers of a diagonalizable matrix is diagonalizable. Then Alireza asked about the product of diagonalizable. In general, is not going to be true. But you see what the problem is. The problem is that this is working. So why is this working? This is working because P minus 1 and P will cancel. So if you multiply A times B, maybe you use a different P. And so it, in general, is not going to be diagonalizable, okay? So again, in general, A and B diagonalizable, in general, does not imply that the product is diagonalizable. No. And Sofia Carnauck has a question about the eigenvalues of the square. So what is true is that if lambda is an eigenvalue of A, then lambda square, or if you want lambda m, is an eigenvalue of A to power m. This is simply because AV is equal lambda V, means that A mv is equal lambda mv. Very easy to see. And so this is why you have this implication. Okay. Any further doubt, question, or remark? Powers keep diagonalizability, alireza, yes, but addition and multiplication does not. In general, that's what it happens. Yeah. Okay. If you don't have any further doubt, question, or remark, we can just call it a day and say that we meet again next week. Okay, so looks like all is fine. No other question, doubt, or remark. So we meet again next week. Good.